once. Sorry not to come in, but I feel like I may be getting sick, so I didn't want to expose everybody to if I hope I'm fine, but if I'm getting sick, I don't want to get everybody else sick. Almost there. Well, should be almost there. Sorry, the Zoom thing is still taking its time on this. There we go. Okay, so now I've got the Zoom recording. Okay. Let me make you a co-host. Okay, well. Okay, take it away.
All right. And yeah, you have to mute yours.
No, my like the speaker is off, so I think it's yours. Oh, you're checking like
I mean your microphone. There we go. And oh, wait. So I think we're good now. Do you hear me, James?
You're a little faint, but I can manage.
Okay. So yeah, 'cause I don't have my the good microphone is at home, of
It's
course.
okay. Usually the mic in the laptop is fine.
Okay. Okay, let me start then. This is lecture 13, continuation of the previous lecture, where we were discussing about reaction kinetic models in CompuCell 3D using antimony. And today we are going to build the delta notch simulation, which you probably have seen multiple times by now, but you probably haven't worked with it. So we'll do the delta notch implementation using tellurium in the language of antimony in CompuCell 3D. That requires us to embed this reaction kinetic model into each cell of the simulation. So that's one of the powerful features of CompuCell. And then we will learn about MABOS. Have you heard of MABOS?
I've heard of that, but I don't know what it is.
Okay, so we will learn about what MABOS is, how it works, and transition our delta notch simulation from the reaction kinetic approach to the Boolean stochastic approach, which is what MABOS does, and see if they behave differently and what are the benefits of using MABOS instead of antimony. All right, so last week, or actually 2 weeks ago, you probably have seen this. So the syntax of antimony, specifying antimony models. So you have this basic syntax of arrow, one variable A, arrow variable B. This means that you lose A. You have like a time derivative of A is decreasing as B is decreasing 1-to-1 in a ratio 1-to-1. So for each unit of A you lose, you gain 1 unit of B. And then after the semicolon, you have your rate. In this case, K a constant times the concentration of the species A. You specify the values of the parameters, the initial conditions of the variables, and that's it. This is your reaction kinetic model. And I also believe you have implemented it in CompuCell 3D and plotted the results in the player. And I'm not sure if you did this. Did you embed a reaction kinetic model into a cell? No, not yet?
Yeah.
Okay. So we'll start today with an exercise, which is taking this tellurium model and embedding it to the cells of our simulation. And I think I have instructions. Right. So these are the instructions of the exercise, and I think I will split screen and open to edit on the right side. Do you think you can do this, or do you want me to show you how to do it before you do? Okay. You can always use the to edit snippets. So for example, in CC3D Python, SBML, you have all these options: add SBML to cells, add SBML to cell types. So you have all these options in your CC3D Python code snippets.
You don't need to specify the initial condition for A and B. Just a random.
You have them specified, initial conditions, so you have A equals 10 to the 7, 10 to the 7. It's already there.
Okay.
A and B. Yeah. T. What's T?
Have this line of code here. And I specify the model name, the cell ID,
Mhm.
and run the simulation, just reports cannot find free floating.
Mhm.
Yeah, that's what I put down, and I delete all the like additional.
Right.
elements.
Yeah, but I think you deleted too much. So I'm going to try something different because we don't have a, oh, what am I doing? Oh my God. Command
Z.
Command Z. Oh, all right. Okay. I'm not very experienced with. Oh. Okay. So, what I'm guessing here is that we don't have a model name equals model, but we do have the model string.
Oh, it's a string, not me. Okay.
Yes. So we should reference, it's Command C, right?
Yeah, control.
Ah.
I need a copy.
Yeah. Command C, Command V, and then this, I guess. And then let's do this. Well, you know what to do now. Yeah, that's what I'm guessing. Free floating model 2.
Do you think it's possible that the remaining code? Because I didn't see like anything related to free floating model.
No, it's add antimony to cell. Let me check that. Add antimony to cell IDs. Model string equals model. That's correct. Cell IDs equals. So it's complaining that there is no. This doesn't exist. Is that? Let me check the error message again. ID equals model.
Oh, public here.
Oh, it's in another.
Like do you think this is anything to do with but we can just comment that out.
What's the line it's complaining about? What's the number of the line?
You see, like, so when we're trying to add data point to the plot, and here for its
Line 66.
yeah, and here
Okay.
you can see this.
Oh, okay.
Solver ID.
Okay. So line 66. SPML dot.
Or we can just try to comment that out.
Yeah, let's for now let's leave it out.
No, but it wouldn't add any data point to the plot.
Yeah, that's okay. Also because since now we have a Tellurium model for each cell, having a single plot doesn't make much sense because we have many cells. That will be either many
Oh.
plots or many curves in the same plot, which is fine, but we will do it in a better way. By using tracking fields.
Mhm.
So, to load the model into cells, this you already did. We have these commands, so you can add to cell IDs. This is what we were doing. You can add to cell types. So all cells of a given type will have the embedded reaction kinetic model. And you can also add to a cell object rather than a cell ID. So cell ID is a number, but in CompuCell, when you do, for example, for cell in self.cellList, this cell thing is an object, it's a CompuCell 3D object. So you can also add the antimony model to the cell object itself, and instead of the ID of the cell, because sometimes you don't have access to the ID of the cell. Or it's annoying to get the ID of the cell. And also you can add to all cells. So to do that, you just do for cell in self cell list. So you're scanning over all cells and then you do add antimony to cell. Here is basically the same command as this one. So you're adding antimony model to a cell object. And then because you are scanning, you are looping over all cells in the simulation, this adds the antimony model to all cells. So there are these different options. For now, I want you to use the last one. So it's cool that you have that, the per ID, but for now, let's add to all cells of the simulation, which is what we want for the delta notch.
But you also like specify the cell equals cell 20.
No, this is a, sorry, this is a mistake. Let me,
Okay, so how do you specify where you just remove the argument here?
so the thing you have, if you look at the slide now, oh yeah, this is just add antimony to cell, and then instead of the thing you deleted, you have cell equals cell, like this. So this argument is the same as the variable of the yeah. How about I show you here? So this argument here, cell equals, oh my god, cell equals cell. This argument here, oh, cell equals cell is the same variable that you were looping over.
Iterate it. Like,
Yes, exactly.
okay.
So it was cell 20 before because I guess I simply copied and paste the line above and then didn't notice that.
Indentation.
No? Yeah.
I think it's
Yeah. Yeah, it should run. Yeah.
But there is no plot, right? And
Yeah,
yeah,
it's
you
fine.
didn't add
Yeah.
any tracking field.
Yeah. You can remove the plots for now too. In the code. And you also don't have cells. What's going on? You don't have any cells?
Probably because I didn't have it initialized.
Oh, okay. So let's add that. You can go to CC3DML, yeah. Steppables, but whatever initializer. Probably
I didn't
the
have
other
those
one.
plans.
But this is fine.
This
Yeah.
is fine.
Yeah, this one is fine. Cell type 0 medium. Yeah, you have to add another cell type. CC3DML again. Plugin. Cell types. Cell type. Replace. Add another one. Yeah, it's going to overwrite everything. Yeah.
And
Now you have cell. You have to close the types situation. What happened there?
no, because I
Oh.
didn't have any style, so it
Oh
didn't-
yeah, I recommend you redo the blob initializer because maybe something screwy. Yeah, this is definitely let's redo it. It goes to C3DML.
I think it probably works. Let me try.
Okay, you can try, but you have to yes. Cell with
Okay.
7 radius 40. That seems fine. Okay, let's try.
Um,
Okay, it's complaining that B0 is missing a value. Go to your antimony.
mhm.
Scroll up. B0, give it a value, whatever
Okay.
value instead of B0, yeah.
It works.
There, run. All right. Let's add cell constraints just to make sure they behave. No, in the XML.
Oh, okay.
Let's do, yes.
Wow.
You can do volume and surface.
Okay.
Yeah. So target volume, that's fine. And then the surface for this target volume would be,
Do you want to modify the values here?
if your cell volume is 50, what would be the appropriate target surface?
Okay. Let me try. Let me try telling. So
You can calculate it.
oh. I think it's around 30 or okay, let's go 30. Yeah, it was fine.
Yeah, that's fine.
Okay.
But usually we do the calculation.
Uh,
Which, so to make your cell behave like very nicely, like imagine you have, because we are in square lattice, assume it's a square,
mhm,
you have the volume of the cell, and you want to find the perimeter.
mhm.
So the side is square root of p. So your target surface is 4 times square root of v. So if v is 50, let's say it's 49, to simplify.
Mhm.
Square root of 49 is 7,
Seven.
then it's 4 times 7. This is 20 something, 28. 28, thank you. So 28,
it's around
yeah,
30.
30 is fine. That's why 30 works.
Yeah, because I'm using 2 times pi times the radius. So oh,
That doesn't quite work because we are in a square lattice.
Okay.
Oh, yeah, we can't even see that properly, but I think you got the idea. Yeah, it's a square, unfortunately.
Okay. Mm. Which one?
Yeah. And if you want to be really obsessed, you can set the target volume to 49. Yeah.
And so now we're going
Yeah,
to add the
perfect.
tracking field, right?
I did more cells though. It's too few cells. Go to radius up to 50. Oh, wait. What's the size of your, let's reduce your lattice dimensions to 100. And then your radius there goes to 50.
Okay, but we need to
And the
modify
center
first.
is 50, yeah. I want a nice, like good density.
Why it's not here?
You didn't create a self?
No,
And you didn't throw any error? What the hell?
I think it's here on the.
Yeah, maybe that. But it would have thrown an error, I think. Oh, yeah,
I think it's because
makes sense.
it will fill the lattice, so we're just not creating cells here. But if you like minimize the radius a little bit,
Mm-hmm.
and the
Yeah.
cell just reappear,
Yeah.
it works.
The other thing we can do is decrease the width to 6. We will have more cells and they will grow and grow to confluence. This is a trick I usually use.
Yeah, you have more cells right now.
Yeah, and then they grow a little bit. Yeah, if we go to a little bit less, like the 5, width 5, you might reach confluence.
Oh, that's so strange.
Yeah. Okay, this is good enough. Now, oh, and you don't have periodic boundary conditions? But this is fine. Let's see what happens. I haven't tried delta notch without a periodic boundary conditions. I think it will be interesting. So let's see. Next step. We want to see what's going on inside each cell. So we want to track the concentrations of the species of our reaction kinetic model. So to do that, there is CompuCell is very smart on this. You just use track attribute cell level, and then you give as the attribute name the name of the variable you declare as a dictionary variable, and then it automatically parses from dictionary to the tracking field. You don't need to do this manually, which is really neat. So this is how you set up in the init. You will have the tracker for each variable. And in the start function, you declare your dictionary variables. And then after you have that in the step function, you update the values of your dictionary variables, and voila. That's all you need.
But why like the value for A and B are 0?
Well, let's check your tellurium model.
Is it because I didn't update the value?
Oh, yeah, yes, correct. Yes. So let me go to the next slide. Yeah, you got a good point. In your step function, we update. And so to update the model, the variable, we have to retrieve the species concentration from the embedded reaction kinetic model. So there is this command cell, which is the cell object, because we're scanning, we're doing a loop over cell. So cell is our cell object. So we do cell.sbml. This is retrieving the tellurium model. And then because your cell could have many tellurium models, many antimony models, sorry, embedded into it, you specify what is the name of your model. So dot the name of the model. Yeah. That's why. So here you have to say like, let me check on mine because I think I have that. Model underscore name. equals, and then you give it a name.
Mm.
There, exactly. Model underscore name equals, and then you give it a name like model one, model whatever. Comma.
Oh,
Right. Now when you reach in the step function, when you retrieve the value, you do cell.sbml.model1. Then square brackets and the name of the variable. SBML dot your model1, square
Model one.
brackets,
okay.
square brackets, and then quotes A. And same for B. Yeah, there we go. Now it should, yeah, Compicel handles the parsing in the background. So we should work now.
Delete the A. How is it? Because the A has an initial value over to.
Yeah, but there is something else going. Oh yeah. So let's do something different. Because you see the maximum here is changing, and the maximum here is changing. So this is between 0 and max. This is between 0 and max. If you want things changing smoothly, you want to fix the max. So fix the max to 10 to the 7, because I think that, or go to your model and set the initial value of A to 1,
This one?
because 10 to the 7 is kind of nuts. So A equals 1.
Mhm.
And go to your player, tools,
Mhm.
tools, yeah. Huh. Okay, click OK.
Mhm.
Yeah, let's okay, you have to reload the simulation. Reload. Yeah. Open it, yes. Now go to tools,
Mhm.
fields. Nice. Okay, so now go to field A or B, field name,
Mhm.
V,
Now
A,
it's
whatever. Then fix max,
Oh, okay.
and now choose field name A. Yeah, fix both. Field A, fix, okay. Now run.
Reload it or?
No, just run.
Okay.
Yeah.
Uh,
It's not changing the value for some reason. Oh, it is. Oh, this is not fixed.
because you fixed the max as 1 and it's not 1 yet.
Go back to, oh, A is changing. So it didn't apply to be, okay, go back to tools. I think I know what's going on. Yeah, fix and click
So
OK.
you need to pick, when you switch a field, you need to click.
Yeah, click OK. Yeah, this is annoying. Very annoying. Yeah, but that's, yeah, it's working now.
Mhm.
So this is great. Let's rerun just to see.
Mhm.
Yeah, rerun. Stop and play.
Sorry. Every time I have to like reload.
Yeah. It should be able to memorize like the,
Oh, wow.
yeah.
Remember this, but okay, let me just try step.
Yeah, there we go. Let it run.
Yeah, I think. Okay.
And you see this one will shift to blue, this one shift to red.
It's not a gradual process. You see, like it's still.
It is very gradual.
It's because like the.
Could you screen share so I could see what the,
Okay.
Oh yeah.
It's already like on.
Yeah, it's orange. The
can
other one
read
is bluish.
I'll write it.
Mhm.
Oh, okay. So,
You should be able to see her screen now, James.
mhm. It's already turning to orange,
Yeah,
and this one is also like not the original blue anymore, but
yeah,
do
let
you
it
wanna?
run.
Okay,
Keep running.
okay, so
Yeah.
I think it works correctly.
Yes. Yeah, this is correct.
And it's lighter.
Yes. So this is the basics we need to build the delta notch simulation. We basically have everything here. The only now so the setup is there. Now we are going to change the equations to the delta notch equations.
Mhm.
And we are going to add a loop over neighbor cells because the delta notch is an interaction between neighboring cells. So there will be we'll develop a script to do that. But fundamentally, this is what you have working here is the like it's the same setup. In each cell, you have an embedded tellurium model, and yeah, they are independent. All right, let's proceed. So I think this is oh, I think that there are more exercises, but I think we rather switch topics to delta notch because they're more interesting and we can do these kinds of exercises using the delta notch simulation directly. Okay, so delta notch are transmembrane proteins. They have a ligand component outside the cell membrane and an internal component. These transmembrane proteins, they have multiple parts. So the outer part is the ligand, it binds to other ligands of other cells. And the inner part, the inside part, can do other things. For example, bind to molecules inside the cell. Sometimes they cleave, so they detach from the transmembrane protein and do something. So both delta and notch are transmembrane proteins, and they bind to delta or notch proteins of neighboring cells. So they require cell-to-cell contact to interact. And this interaction determines the phenotype of the cells. They change the fate of the cell, and this is important for cell differentiation, and it is important for developmental processes. So one interesting thing here, and which it's what we're going to focus on, is this type of patterning where you have the cells arranged as one central cell surrounded by cells of another phenotype. So this is inner ear of Drosophila, and I think this also happens in human ear, where you have a hair cell as the central cell, and the neighboring cells are supporter cells. I don't know the details of what each of them are doing, but the delta notch is this kind of interaction, cell-to-cell interaction, that guarantees that you have this heterogeneity in the tissue. So cells will have different functions, and this is important for some developmental processes. So because I am not an expert in delta notch, I won't talk about the implications, all the implications in development. So James, if you have comments to aggregate to the importance of delta notch in development, feel free to.
Well, it's a pretty universal mechanism. You see here the hair cells, it happens in the eye, it happens in the lining of the uterus, it happens in blood vessel development. And so delta notch is one of the main spatial patterning mechanisms for contact signaling in development and also in wound healing.
And it can produce various kinds of patterning. So this is not the only one. There are other kinds that and they use the same set of interactions. And you will see how using the same model, just by changing the parameters, you can get very different types of patterns in the tissue, which is very interesting.
Another thing is that this model is going to give us a stable, a relatively stable spatial pattern. And in development, normally the cells achieve a stable pattern, but our collaborator, experimentalist Lorenzo Meschini, has shown that under certain circumstances, delta notch signaling can also lead to oscillatory expressions of delta notch. So it's also possible for that to happen.
So how does this happen? So both delta and notch are transmembrane proteins. They have an internal and an external part. The external part is the ligand. The ligand of delta binds to the ligand of notch across different cells. And when that happens, the inner side, the inner part of the notch protein cleaves, travels into the nucleus and disables expression of delta. So a cell that has notch cleaving because of this interaction will express less delta as a consequence. Delta, on the other hand, binds to notch in the same cell and inhibits this cleavage of notch. So a cell that has a lot of delta will disable this notch cleavage and traveling into the nucleus. So in the end, what happens is one cell will become a predominant delta expressing cell, and the other cell will become a predominantly a notch expressing cell. So this is called mutually exclusive cell fates or phenotypes, mutually exclusive phenotypes, and they are stable. So once one cell has high notch, it tends to stay high notch because it's disabling delta. And the cell that has high delta is disabling notch and tends to stay that way. Of course, if you have two neighboring cells and both are high delta, or both are high notch, there is an instability. So if you introduce some fluctuation, for example, if you introduce like an initial randomness, like all cells are high delta, but there are some fluctuation, like some are like 0.9, some are 0.95. The tendency is that some of the cells will win, some of the cells will lose the competition, and in the end will have the same fate of some cells being notch, other cells being delta, and they intercalate. All right. We will use a very simple model. There are many ways you can model this interaction. And this interaction can be very complex, as complex as you want, because you have ligand binding. So you can write an equation for the rate of binding and unbinding of these ligands. You can write an equation for the rate of notch cleavage. You can write an equation for the rate of binding between delta and notch in the same cell. You can write an equation for notch nuclear import, notch disabling transcription of delta, transcription and translation of delta and notch, degradation of these receptors. So you can write like complicated equations for each of these processes. This very simple model we are going to use pays attention just to the cross inhibition. So this is so it's the only thing it has is this cross inhibition. You have a basal rate of production of delta and notch and a basal degradation rate. So you have a positive term for both. So this is adding to the derivative. So delta is growing with this term and notch is growing with this term here. okay? And you have a degradation term. So minus D and minus N, these are both degradation terms.
So the N and the D at the first term are for the neighboring value, right?
Yeah, I'll get there.
Okay.
So for now, just imagine that you have like this full thing here equals your production rate. So I will write like your production rate. Your production rate in this case is a function of notch, but it's just your production rate for now. And this is also your production rate for notch. So this is your production rate for delta. This is your production rate for notch, and it depends on the hat, whatever. So you have production minus degradation. Okay, degradation is proportional to how much you have of that. So D equals minus a constant times D, and N, derivative of N equals minus a constant times N. So degradation is proportional to the concentration of the variable, and you have a production term. So now imagine, the way I like to think about this is your production term is 1, but then it's multiplied by a Hill function. So it's being modulated by another function. Same as here, your production rate of notch is 1, but it's modulated by a Hill function. Okay? And these Hill functions are the activation / inhibition of delta and notch. So delta in other cells do what? They cleave notch, release notch into the cell. So the production rate or the availability of notch inside the cell is proportional to the concentration of delta in the neighboring cells. So the more delta you have in the neighboring cells, the more notch you release inside the cell by this cleavage process. Okay? This is an excitatory Hill function. So the more delta you have in the neighboring cells, the more notch you release in the cell. Okay? So as an example, you have a cell here, and then you have like the neighbors. And the average is the average delta across all these cells here. The higher the average, the higher notch you have in the central cell, and the lower the the faster the release of notch, and the lower the average, the lower the release rate of notch inside the cell. Okay. In the case of delta, again, you have your production term is 1 times something, and this something is an inhibitory Hill function. So this Hill function is going down as n increases. So and n here is the notch inside the same cell. So the more notch a cell has, the lower the production rate of delta. All good?
Yeah.
Nice. So I think we got this.
Yeah, you answered my question.
That answers?
Yeah.
Fantastic. Okay, let's keep going. Yeah. So this is your exercise. You can use your Biggie simulation and ignore some of the instructions. So you already have your lattice. You don't need to do 42 times 42. You can use your own. But for example, implementing the delta notch equations you have to do. So I'll leave it as an exercise. It's can be tricky to write down these equations. So I'll give you some time to do it, and then I'll compare yours to mine to see if you didn't make any syntax mistakes. After you have the equation set up, you write the loop over cell neighbors. And I think I have instructions on the loop over cell neighbor somewhere. Yes, I do. But I'll give you the chance to follow the instructions by yourself for now.
I'm here if you need me. I'm following, but if you'll have my sound off in case, but if you need me, for help or anything, I'm available. Okay.
Okay, thank you.
Right. I'm good. I think there is an exponent for D. Ah, and in J4, there is no underscore.
Oh,
Yeah.
I'm using this to represent the average from,
No, but look, this is a variable, not a parameter. Okay.
Uh.
This is delta inside the cell.
mhm.
So D.
Um,
Oh, wait a second.
but the D is from,
Oh, no.
right, D is from, like, so how do you write this function?
Yeah, I see though that there's a problem here. Uh,
Because this is easy, but
you don't have mass conversion between notch and delta.
what is a mass conversion?
Mass conversion is like a transformation of notch to delta and back and forth, or delta to notch. Like notch doesn't convert to delta. So this is what this equation means. This equation means that notch is becoming delta.
Oh,
See? So if you don't want notch converting to delta, you just remove this, and now you just have delta is coming out of nowhere.
I see what you mean.
And then you have a rate of delta coming out of nowhere. Yes, there we go. Yeah, now it makes sense. Yes. So delta is, yeah, you just need the exponents for D underscore, yeah. Mhm. Uh,
You have to
oh
visit.
no. Well, you don't need for the average. Yeah, the average. You were trying to do tracking fields for the average?
No, this is, I need to initialize the definition for, oh yeah, I don't have to. Why would I need to do it here? I need to visit all the snake list.
Yeah.
Uh, mm,
Mhm.
mm, neighbor. Mm, Um,
Yeah, you want to pass this average. Oh yeah. Yeah, exactly.
neighbor
Yeah.
dot the D else just we just delete that
Mm-hmm.
and just calculate. Oh, and we need to like calculate how many neighbors it have.
Mm-hmm.
Neighbor plus 0 neighbor count. Finish their version. So dot to C underscore equal delta divided by neighbor. And we need to copy this. This into our step function. Yeah, I think that's it.
Okay, before we get there, make sure you have the same constants.
Oh, okay, yeah. We do.
What is A?
A is
Oh,
0,
okay, yeah.
and
Yeah, set those values.
what is created? Oh, it's ordered. Oh,
And are we still here? You have to initialize the underscore.
yeah. Hmm?
Yes, the underscore.
Oh, but we don't
And this is
calculate.
not an initial condition, it's a parameter. The underscore is a parameter.
Okay. But what is? Let's just use as 0, right?
Yeah, it doesn't matter the value because we're going to reassign it, but
Okay.
Tellurium will complain
Okay.
if you don't have any value for it. Yes, I think, let me just double check real quick, the Tellurium one, the antimony. Oh, yes,
Mhm.
that's also important. Yeah, okay.
You want to play it?
Exponent for the underscore,
Oh, okay. Here?
line 11.
11.
Yeah. D underscore to the power of K. Yeah, D to the power of K.
Oh, okay.
Yeah, you need that.
Oh, yes. Let's ignore it.
Looks correct. KH. Yeah, it looks correct. Okay, let me.
The only thing is I didn't randomize the initial
Yeah,
value. I just picked.
let's not worry about this for now. We did this. Slightly different way of writing things in the slide, but it's fine. Who cares? So in the slide, you have the Hill function for the average minus n, and for delta, you have the inhibitory Hill function minus D, and V multiplies both terms. Either works, it doesn't really matter. Initialization for the average D and N here. And variable, oh, I usually call these variables and these parameters, but it doesn't matter too. All right, this is what we did. What you have, it's working. In the start function, you do add antimony to cell.
Oh, I didn't initialize that. Start and I just, but it's okay, we just,
No, scroll down,
oh,
stop. Line 58, you have it.
wait, why did I do that? Uh-oh. Oh, this is.
Yeah, this is kind of weird.
Uh,
Honestly,
this-
you also don't need this for loop over neighbors. Yeah, in the start function, you don't need that.
oh, probably,
Yeah.
yeah. And,
So yeah, here you already have it. So this is what the slides are showing. Add antimony to cell.
yeah,
Here it's using cell types, but it doesn't really matter. You're adding to all cells.
yeah,
This is correct. This is fine. Then you have inside the loop of overall cells, you have cell dict for D for N. You don't need for D underscore, but I think you have another idea for this, which is fine. In your step, you have time step SBML, right?
yeah,
Right.
here.
So now we are doing a loop over neighbors. This is how it was implemented. It's yours doesn't work so far because you are not retrieving the values of delta in the cell neighbors. When you do neighbor.dict D,
Mhm.
what's the value of neighbor.dict D? That's 0. You initialize that as 0, right? Oh, no, you
No,
are
I
updating
already-
here.
Yeah,
SBML.model. Okay. So I think yours work. Let me just take a look real quick. For cell in cell list, cell dict D equals, so you do all the assignment. No. Yeah, no, doesn't work. You know why? Because take, for example, the first cell. You are doing it for the first cell. So you're updating the values of delta notch for that cell, but you didn't yet update the values of delta notch for the neighbor. So delta notch for the neighbors is still 0. So the way you did doesn't work. What you want to do instead is when you do the average, delta, and let's call it delta average. Oh my God, I hate math. Let's, oh, you do it. Delta average or delta underscore AVG, whatever. Call it delta underscore AVG
but that, oh, okay,
for delta average, yeah.
okay.
Now you do in line 92 delta AVG plus equals, instead of neighbor.dict, you have neighbor.sbml.model1 SBML
Okay, I see.
dot model1. There we go.
Oh, I see, yeah.
And then instead of 94, what you will have is an
Oh.
assignment cell dot SBML in 94 cell dot SBML model 1 D equals, yeah, that's it, delta AVG, perfect.
So
Now
you're writing,
you were changing the value of D underscore in the central cell, in the central cell.
yeah, but I didn't see like the difference, like why, we add this d underscore value into the SVM itself. Because every time you need to recalculate this value.
Yeah, you have to recalculate it every time, every step, yes.
So you can also just write in the dictionary, not word, not.
No, it doesn't parse. If you write to the dictionary, you have to parse it back.
I see,
in
because
another
it
line.
would not like reload this d
No.
underscore into this.
Yeah,
Oh,
exactly,
okay,
yeah.
I see.
Let's scroll up to your start function. You don't need cell dict d.
Mhm. You don't want
To track it? No.
oh, you don't want to.
No, it's not a good idea. It's a little bit redundant because you already know delta on the neighboring cells. Okay, scroll down. So let me just double check. You have for cell, you were doing the tracking updates, that's fine. Delta average, neighbor average, for neighbor. Then you have if neighbor count. Yeah, that seems fine. Let's run and see what happens.
Okay.
Yeah, of course, it's not gonna work because we have to randomize the initial conditions, but you can run and just to make sure we didn't make any huge mistake.
Couldn't.
Oh, yeah,
Oh, because I didn't add.
yeah,
the-
exactly.
Okay.
Plugins, systemctml,
Mm.
neighbor tracker.
Okay. Load division by 0.
Oh yeah, if a cell doesn't
Because
wait.
the neighbor count is initially 0 and I can't do that.
Oh, I see what's going on. So this
It doesn't have any
is
input.
you have to. Huh? No, that's not what it.
What do you want to do?
Oh, this. No, it's correct. Makes sense?
Oh, yeah, yeah.
Can I see be willing to
Yeah.
screen share again so I can see where you are?
Okay.
Yeah, let's try.
Yeah, we should have seen the original vision version. I'll just try to.
Now that looks fine.
No, because figure out a lot
I'll be
of.
back in a sec. I have to step away for 1 second.
No problem, Jigs.
One exercise I think would be useful to do if you're going to do this one.
Mhm.
Also do the exercise where you weight the signal by the contact area. So
Yeah, I was thinking about that, yeah.
that's an easy addition. It's only changing 2 lines, but it shows how powerful some of these techniques are.
Yeah. That's fine.
But no, it's not. Because,
Why not?
because D and L, well, let me just restart it in some. C is original like a value near
Yeah.
1 and this is also a value near 1, but they appear. This one's around here,
Mhm.
and this one's around here. It's not very close to 1.
No, but you have that's how you initialize it. You set like 0.9, 0.95 as the initial conditions. Yeah, let's check the Tellurium model.
Okay, so this change. Oh, so this.
Yeah, that initialization.
Okay, now. Oh, okay. So this.
Yeah, but yeah, it doesn't matter. It will run again.
Okay.
It's still going to have the same. Like, of course, they will look different. And I'm annoyed that it doesn't open the windows for us.
Oh yeah, okay.
And you can have just 2 windows because this one is meaningless anyways.
Mhm.
Yeah. Yeah, 0.5, 1 wins, yeah. Notch wins. Because notch inhibits delta, and that's it. Yeah.
Okay.
So why is this happening? Why we don't have patterning?
Mm. Mm. Because we only have rules for the cell to detect the neighbor, the delta of the neighbors. We don't have like um wait, let me think about that.
Do one experiment and then to help you understand why it's not patterning. For one of the cells, I want you to do cell.sbml for just for one of the cells. So after the for loop, let me do a little bit of a cleanup here.
Mm.
Can I delete stuff?
Yep.
So here I'm going to do cell. It looks weird because it's outside the loop, but it's basically just taking the last cell of the loop, so it's a single cell. Model 1, right?
Mm.
And I'm going to do d equals 0. Command save. And run again. Let's have just 2 windows now. Yeah, we could have just 1 window even, but this is fine. Yeah. See this one? The
Mhm.
last cell of the loop has 0 delta. Let's run it, see what happens.
Mm. Um,
Division by 0.
which one?
Neighbor.
Neighbor.
So that there is a cell with a, oh, you see this one?
Mhm.
I think it's this there's a rogue cell here that probably this cell deleted a pixel here that had a neighbor contact and fucked up. So add an if statement there saying if neighbor is 0, you skip this shit. Neighbor count +1.
Line
In,
66, yeah.
yeah. Because we didn't reach confluence, so there is this annoyance. If neighbor count, comma. Yeah, if neighbor count,
Oh.
yeah. I indent that. There we go. And let's run it.
Mhm.
So we have what I'm doing here, James. I think you probably James understands what I'm getting to. Is that if you start with a single cell, just a single cell with different stuff, run it and see what happens. We have the patterning emerging and propagating. But in the previous one, we started with all cells with the same amount of delta and notch, and we did not acquire the pattern. Why is that? That's the question I have for you.
Okay, I'll need time to think about that.
So it's something related to our initial condition, right? Because we didn't change anything in the model here. We just changed the initial condition.
Yeah. Mm.
And it's more beautiful, James, starting with a single cell.
Yeah, because you could see how the pattern adjusts to the proliferation and the change of density and all of that. Yeah.
Oh, I quite okay. I don't quite understand because at first you can see like all of the cells have the same pattern, and after a while, and then begin to have this pattern. But at early stage of the simulation, it didn't have any pattern, right? Just like identical.
Go back to your code, start function, and that's the line 50, comment out line 50. And run again. You can leave just one and choose yeah, and let it run. Nothing happens.
Delta is 0.
Yeah,
Oh,
nothing happens. It's just that line. What's that line doing?
uh, so
Oh, we have okay. But this is probably from numerical fluctuation of the method. So what's going on here is if you set all deltas and notches to the same value among all cells, they equilibrate. They are in equilibrium. It's an unstable equilibrium, but they are at equilibrium because they have the same signal. So it's the same force against the same force. But if you start with them slightly different, one wins because it's unstable. It's an unstable equilibrium between neighboring cells. So you start with a single cell with a different level of delta. It cascades and breaks the equilibrium across the system. If you start with all of them the same, they stay the same. It broke symmetry because of numerical fluctuation. So the method, as it runs, probably there is some numerical stuff going on, and then eventually it broke symmetry.
but if it's that cell triggers the
It's not a bad idea to add a random number, a small random number in lines 44 and 45. When you do the initialization, you could add the 0.5 plus or minus some small random number. That'll do it too.
Dot uniform. Yeah, and p dot random dot uniform.
the it would be like a really small
0, 0, 1, and then you delete the 0.5. So it goes from 0 to 1, your random variable.
okay.
Yeah. That's enough. That will do the job. They'll start with different concentrations.
The delta here it's all 0. And
It didn't work.
and like just
So the
just a
random,
while, just like space pattern.
did you save the simulation?
Yeah, I think so. Yeah.
And
Yeah, you
that's
see like
random.
the pattern just show up. So my question is if this it's a like one single cell with different status affect the whole pattern, so why would it like appear afterwards? Like after all of the cell have a delta value of 0 and then last for like a couple of monoclonal steps and p space just this space pattern just show up again. So that's the thing that I don't understand.
I don't understand your question.
So as you said, like we're setting all of the like the delta,
Mhm.
initial delta is 0.5 and it's equal to the notch value.
Yeah.
And we see like, so the early simulation stage, all of the delta are 0 for all the cells, right?
Yeah.
And after a while, they just have this,
They emerge, yes. The pattern
yeah,
emerges.
emerge of the pattern. So, and then we switch to a condition that we have a cell like with a different initial state, right? Like,
Yeah, not in this one.
yeah,
Not
not for
in this
this
one, yes.
solution. But we also observed that at early simulation stage, all the cell like have a stage where all the cells have a delta of 0, right?
Not exactly 0, but
Oh, you mean
very
like,
close to 0. Yes, very
you mean
close.
like they probably have a very,
Yes.
oh yeah, that's possible. And okay, in that way. But we need to like verify if they're exactly 0 or
Like if you set them to 0, 0, so set
okay.
yeah. And then notch 2.
No.
Also notch 0.
Um,
Yeah. They are going to stay like that. Nothing changes.
okay. Yeah.
Yeah. Nothing changes. Theoretically. Like there could be numerical instability and like eventually a fluctuation makes the system collapse. But theoretically, it stays like that forever. Because all the variables are the same. So it stays like this forever. Once you introduce some fluctuation, yeah, I think this is numerical fluctuation. Yeah. But once there is a slight, like a very, very minor difference between these protein levels, the system will collapse to this pattern here. Because you have two cells together and one has like a little bit more delta than the other one. The one with a little bit more delta will become the delta expressing cell, and the other one will become the notch expressing cell because of the cross inhibition.
So another question is where is the numerical fluctuation coming from? Like,
I believe from the solver from
so
how's it called, lib road runner.
from, because it's a like iterative way to have have the solution for the ODE.
Yeah, it's the OD solvers probably has some instability, some fluctuation. Yeah. For example, even I remember running a very simple ODE, and then you zoom in a lot, and then you don't see exactly a straight line. You see something going up and down if you zoom in a lot. So probably that's uh growing and growing exponentially because of the system we are dealing with, and then it becomes the pattern emerges from that.
Okay, and if we just introduce the difference between delta and notch at first, we will just speed up the
Yeah,
fluctuation.
yeah.
Oh,
That's why I like line 50. That's my
Oh.
favorite one. So if you set a different value there, so we will uncomment that and say this is anything other than 0. Yeah. And run. The pattern will propagate from that cell.
okay.
Yeah, that cell is in the upper right corner, and then the pattern will emerge from that cell and spread.
Cool. So this is very small delta. So would notch have the same effect of triggering?
Yeah.
Because we could see like a very small delta, even like a fluctuation that is probably like very close to zero would intrigue all of, would
Yes.
trigger all of these. So for notch it has the same impact.
Yes.
Mm,
Yes. As long as you have any difference between two neighboring cells, they will collapse. They are mutually exclusive phenotypes. One is going to be the notch expressing, and the other one will be the delta expressing.
I see.
So any small difference between neighboring cells will collapse the system, and the pattern will propagate.
So from the perspective of the equation, that means the equation, like the reaction is very intense.
Yeah,
Okay,
it's very unstable.
okay, I see.
Yeah, having the cells the same phenotype is very unstable. Any minor fluctuation will collapse and break the symmetry, as we usually say.
I have no question.
Hmm?
I have
Go
no
ahead.
question.
Yeah.
Oh, I have no questions.
Oh, no
Mine
more
is
questions?
not
Okay.
clear. Thank you.
All right. I hope you're having fun. Yeah. And now we are going to explore this. No, first we are going for a break. Okay, so if you want to go to the bathroom, I will go to the bathroom. We'll do like a 10 minutes break. I'll be back, James. All right. So the next part of the lecture is substituting our Tellurium model by MABOS model. And so MABOS is Markov Boolean Stochastic Simulator. It is a C++ software to model Markov chain Boolean stochastic networks. This is the website, and this is a diagram of usually what people teach on Markov chains and Markov processes. Like you have a system with different states. So for example, imagine a person can be happy, sad, or bored. And the person transitions between these three states with certain probabilities. Okay? So for example, if a person is sad, in this diagram, there is a 50% chance they remain sad. And then there is a one third chance they become happy, and 1/6 chance they become bored. Here, 1/6 plus 1/3 plus 1/2 is 1. Okay, they have to add up to 1. And the same applies for the other processes. So for example, if a person is happy, there is a 2/3 chance to remain happy, so on and so forth. So all these states are connected. You can go from happy to happy, from happy to sad, from happy to bored, and all different combinations. Okay? And then by changing these probabilities, you can measure, for example, how much time a person spends happy, how much time they spend sad, how often they transition between these states. And yeah, it's very useful, but it is stochastic. So you don't have, for example, an inherent time a person spends in each of these states. So for example, if someone is sad, it makes sense that they will be sad for, let's say, at least 30 minutes before they can transition from sad to happy or bored. But from the perspective of the Markov process, we absolutely ignore that. So these 30 minutes minimum of sadness, it doesn't matter for the Markov process. A person in the Markov process, a person can be sad for a second and then transition from sad to happy. Okay, so it is a simplification, but it is very useful for many applications. All right. If you don't care about the species when you're modeling for example, a signaling network or a metabolic network or a gene regulatory network, if you don't care about the amount of that species in the system, a Boolean network is a very good approach, because the state of that protein can only be true or false, can only be a Boolean. So for example, imagine you have like a DNA damage network. Either the DNA is damaged or it isn't. Okay, there is no in between. There is no like semi-damaged gene. Either it's damaged or it isn't. Okay, of course you can discuss about like degrees of damage, but if you're developing a simplification, it is very reasonable to treat the DNA as either damaged or not damaged, right? And similarly for other situations, for example, apoptosis, either the cell is apoptotic or it isn't. Usually we don't talk about in between, like different levels of apoptotic cell. That doesn't, I mean, you could discuss that, but usually for the purposes of our models, we don't really care about these different levels. Of course, let's say you are talking about delta notch, for example, maybe you do care about the level of delta, about the level of notch. Maybe you do care about that. Maybe you don't. Maybe you just care about whether delta and notch are true or false, because the outcome is a cell with notch expressing or delta expressing, right? So it depends on the level of detail you want for your model. Okay, so the Boolean network will have less detail, will be more simple, and usually will be faster in terms of performance, computational performance. Your model will run faster if you have all your networks in MABOS rather than Tellurium. Okay? So as a network, you have the nodes. The nodes will represent, for example, your protein, your gene. They might represent a phenotype. So you can have a node be, for example, apoptotic, could be a node. It's not, apoptotic is not a protein, it's not a gene, it is a phenotype, right? It's a behavior. So you could have a node be a behavior, okay? You have your arrows of your network. These will be the interactions between the nodes. And these interactions will take place, for example, between different proteins or also between proteins and phenotypes. So for example, you could have caspase, which is a protein, pointing to apoptotic, which is apoptotic is not a protein, it's a phenotype. So you can have all these interactions represented as arrows. And in the case of a Boolean network, you don't have rate equations. So you don't have like the production rate of a protein. You have the activation probability of that node, okay? So in a very simple case, for example, you have protein A activating protein B. In a Tellurium model, you would write protein B is increasing and you write the rate as, for example, K times A. In the case of a Boolean stochastic network, you have, if A is true, there is a probability P that B goes up, okay? And as you iterate as you progress in time, you will sample random values, and depending on that probability, your protein B will transition from false to true and will become active. So far, so good? So very, very simple. So they can be appropriate for modeling gene regulatory networks. And a few examples, for example, DNA damage is an interesting one because it's probabilistic, because it's Boolean, you know, it's either true or false. Protein signaling is more debatable, whether you should use stochastic Boolean networks. But in certain cases, for example, caspase signaling is basically Boolean. If the cell is producing caspase, it's going to die. If it's not, it's fine. All right. I don't know what happened to the slide, but this is one example. This is a paper using MABOS to simulate. This is DNA damage. No, DNA damage, and then the cell might die in response to the DNA damage. So this is not an agent-based model, so this is not using Physicell or CompuCell. This is not embedding to anything. This is just like hundreds of nodes, hundreds of proteins, and they are all interacting. And then you can use this to measure, for example, how often something will happen. So given all these interactions, all these nodes, how often will the cell die by apoptosis, or how often the cell will die via ferroptosis? Okay, so you can measure these ratios of cell phenotypes which often the experimentalist will give you. It's usually rare that the experimentalist will give you the concentration for a protein or the level of a certain cell phenotype. Usually they tell you 10% of the cells are apoptotic, 30% of the cells are ferroptotic, another percentage is that one, so on and so forth. So they don't really give you like a degree of these phenotypes. Usually they tell you like what is the fraction of cells at this phenotype, at this other phenotype. So in these cases, a Boolean stochastic network can do the job very well. MABOS is used in different ways, and you can use different packages to model things. For example, MABOS individually, you can build like this, like a very large network and see like the outcomes of this single network. You can do an ensemble MABOS, so you can run the same network you have, instead of running only once and seeing what's the outcome of that, you can run multiple times with multiple initial conditions and study what is the average behavior of your network and the standard deviation of your network outcomes. So this is ensemble MABOS. These are packages you can access and use. There is up MABOS. Now we are already talking about an agent-based model, where instead of just running multiple times and averaging, you have different instances of your MABOS network and you can have them interact. And you can have different MABOS networks, and these different networks interact between each other. So you can use that, for example, to model an organism. So you have, for example, a Boolean stochastic network for the liver, a Boolean stochastic network for the gut, whatever, and they are all interacting. So you have states for these different organs, and they interact, and based on the state of one, another organ can change. Okay?
Mm.
Or if we go back to our previous example of happy, sad, and bored, imagine now you have two people. They can be either happy, sad, and bored, but they are also interacting. If person A is sad, maybe there is a higher chance that person B goes from happy to sad. Okay? So you can establish these interactions and see how this agent-based model, which is not spatial in this case, there is no spatial aspect, there is no distance between these agents, but it is agent-based model in the sense that there are different instances and they are interacting there. They could exist independently from each other. Finally, PhysiBOS is an integration of MABOS and PhysiCell, so that you might have heard already. So here, now we are talking about a spatial agent-based model. So you have different cells, they exist in space, they have position, pairs of cells have distance between each other. And then you embed MABOS models, MABOS networks into each of these cells.
Mm.
And they can change the behavior of the cell, and whatever is happening in the microenvironment can affect the behavior of these MABOS networks. So far, so good?
So the last MABOS model that you're talking about is related to spatial information.
Yes. So the MABOS component is exactly the same among all these frameworks. It's just how they are integrated.
Okay.
So in the case of PhysiBOS, you embed MABOS networks into each individual cell the same way as we do in Tellurian.
It's just
and
they
this is the-
integrate
Yeah.
spatial into the MABOS.
Yes,
Okay.
exactly.
Thank you.
Yes. The underlying structure of the network is the same, everything about the Boolean stochastic network is the same.
Mm.
And parallel to FuzzyBoss, we have CompuCell 3D, which also allows you to integrate Boolean stochastic networks into cells, individual cells. Okay?
Mhm.
But of course, it's not PhysiCell. PhysiCell is a molecular dynamics like solver, while CompuCell is a cellular POTS model solver. Right. So let's get a little bit more familiar with Boolean networks. So here we have a simple network with 3 nodes, G1, G2, and G3. Each of these nodes can have 2 states, 0 or 1, true or false.
Mhm.
And they have the interactions. The interactions are determined by the arrows. So for example, if G2 is true, G1 becomes true,
Mhm.
okay? Because G2 activates G1. If G1 is true, G3 becomes false because G1 is inhibiting G3. All right? So on and so forth. Obviously, whenever you have multiple arrows arriving at the same node, you have to specify how they interact between each other. So for example, G1 activates G2 the same way as G3 activates G2. But someone could ask, do I need both G1 and G3 to activate G2? Or either one of them is enough to activate G2. Okay? So the AND operator basically is telling me that I need both G1 and G3 to activate G2, while if I said that's an OR, I could have G1 being 0 and G3 being 1, or G1 being 1 and G3 being 0, G2 would activate.
Mhm.
Okay? So given this network, we can write a table specifying a possible current state and what the next state would be. So for the first one, imagine everything is 0. What would happen to the network? So if G1 is 0, G3 can go up, right?
Mhm.
Because G1, there is no G1 to block G3. So G3 will become 1, goes from 0 to 1. What happens? Let's see what happens to G1. So G2 is 0, so there is no activation. So G1 stays at 0. So G1 goes from 0 to 0. And let's look at G2. If G1 is 0 and G3 is 0, nothing happens to G2. G2 will remain 0. So the current state is 0, 0, 0, and the next state will be 0, 0, 1. Now we start with 0, 0, 1. What happens to this state 0, 0, 1? It stays as 0, 0, 1. Now you can run the same analysis. I think at this point it's just a waste of time, but you do this for all of them, and then you see what happens. So once you finish all of this, you will see that there are like a graph, a transition graph. So for example, if you start at 0, 0, 0, you go to 0, 0, 1, and from 0, 0, 1, you stay at 0, 0, 1. This is not written here, by the way. I don't know why. Oh, yeah, it is. It is right here. So if you start at 0, 0, 0, you go to 0, 0, 1, and then you stay at 0, 0, 1. Okay? If you start at 0, 1, 1, you go to 1, 0, 1, and then you keep looping back and forth, so you reach an oscillation. So there are different behaviors here. You can have oscillation. This is an oscillation. And you can have a, something stable, like decay down to a final state and stay stable there. So with this very, very simple system, 3 nodes, you can have like a very rich possibilities of outcomes of this network. However, this one is deterministic. So every time we do one step, we definitely transition to a single one. In the case of MABOS, we can do things stochastically. So instead of doing, we definitely transition, we say there is a probability P of transitioning. And you can also say there is also another probability P to transition directly from this to that one. So, and of course, because it's probabilistic, you run one step and it may or may not do this transition. So sometimes you have to do like multiple steps until you have this transition happening. So there is, when you introduce stochasticity, there is a time component to this transition process. Instead of taking a single step to do the transition, since you have a probability, it might take multiple steps for the transition to happen. Okay? So the probability of this transition determines the average transition time. Okay? The higher the probability, the faster the transition. So the lower the average transition time, and the lower the probability, the higher, the faster the transition, the lower the average transition time. All good?
Yeah.
Okay. So from my personal experience, MABOS is very fast, and it can be an effective alternative to Tellurium if you are dealing with like a very large number of cells and your network is, for example, if your network is very, very big, like has hundreds of nodes, I would say MABOS is probably the way to go. Especially because many times you lack experimental information about the levels of the species, like concentration, production rate, degradation rate. So many times, very frequently, since you don't have this information anyways, it is often much simpler to just say, okay, this is going to be either true or false, I don't care, and there's no experiment to back up my Tellurium model if I build one. Okay. And it's very easy to associate probability rate to time because it's the inverse of that is the average time. So just take your probability rate, you do 1 over that, that's your average transition time. Of course, that only applies if for each Monte Carlo step you step once your MABOS model. If for each Monte Carlo step you step your MABOS model like 10 times, of course you have, then you have to do a Poisson correction of the average time. Coupling MABOS to CompuCell 3D allows you to model a lot of cool stuff. So this is a interesting implementation of delta notch coupled with cell proliferation. You can see that it is Boolean. So you don't have like yellowish, greenish cells. They are all either blue or red. In your Tellurium example, you can have like those yellowish, greenish cells because you allow different concentrations of delta notch. And here they are either blue or red for each of these signals. So here, this model is representing delta, notch, and ICD. And ICD is the part of the notch receptor that cleaves and migrates and goes into the nucleus to regulate cell phenotypes. And then you have cyclin E, cyclin A, B, and CDC20, which are cell growth, cell division signals. Okay, I don't remember what each of them do, but they are responsible for telling the cell to go from like metaphase to prophase to another phase, anaphase, and complete the cell division process. okay? And probably I messed up the order of the cell division. So the syntax for MapBoss is quite simple. You have a node, you open curly brackets, and then you have a logic. A logic will be the we'll use C++ or C syntax for not, and or. So for example, this is an and, exclamation mark is a not, this vertical symbol, this is an or, yeah. Parenthesis, self-explanatory. So very easy to code. These guys here, RB, CDC20, they are names of other nodes.
So these are conditions, right?
Yeah.
Okay. So only like when this condition is true and the following things will happen.
Yeah, correct.
Okay.
So your logic can either be 1 or 0. Okay. So depending on the values of these guys here, your logic will be 1 or 0. Then if logic is 1, so this is a question, if logic is 1, what happens, right? So rate up, which is the probability of going up, will be this number. So this is a variable.
It's a 0, 1 variable or
Between 0 and 1. You can have this being like 0.1, 0.01. You set the value of this parameter. Slow is a parameter. Okay? So if your logic is true, your up rate, your rate up will be this number here. And if your logic is false, it will be this one here.
oh,
Okay? So even if your logic is false, you can have a up rate. Even if your logic is false, you can set
I'll just modify this.
up. Yes, exactly. And then you have a rate of going down. So if your logic is true, you have one rate. If your logic is false, you have another rate. What is cool about this is, for example, if you set a non-zero upregulation rate for your logic being true and a non-zero here, you can have your cell oscillating true and false, true, false, true, false. Because even if your logic is false, you can upregulate. Even if your logic is true, you can downregulate. So you can have oscillation even in a single cell, regardless of what's going on, regardless of the states of other nodes. So this is, I think it's annoying to write this, but the syntax is very, very simple. And then you can specify the initial conditions of your nodes. So basically you write the name of the node dot is state, I state, initial state equals 1 or 0. Okay, and everything ends with a semicolon because this is C language. Okay, so this is something very annoying. If you look here, everything ends with a semicolon.
Well, that's like antimony too.
Yeah, so it follows this idea here. You have a condition. If the condition is true, you have one value. If the condition is false, you have another one.
So like the dollar symbol here is with this low, so that refers to a variable or a parameter.
Yeah. So if you have a parameter, you have to use this dollar symbol to tell MapBoss that slow is not a node. Because if you don't have a dollar sign, it's a node.
Okay.
For example, RB, CDC20, they don't have dollar signs.
Yeah.
So these are nodes. Now, if you want to set like a probability parameter that has a value of like 0.5, and that has a name like slow, then you refer to it using the dollar sign. Otherwise, Mapboss will interpret that slow is actually a node. So far, so good. So yeah, delta notch. This is what we're going to do. To define the delta notch model, I write it like this. So there are different ways of doing it. I write it like this because it is very, very simple and very similar to the tellurium analogous. So basically, I have a D average. This is something you have to inform the Mapboss model from your CC3D level, from your Python level. So you pass your value of the average. And then if this value of the average is above a certain threshold, which you specify, then notch will go up according to what I wrote here. If delta is large, notch goes up. Oh yeah, if delta, yes, if delta is large in the neighboring cells, notch goes up. Perfect. That's exactly it. Yeah. Yeah, it can be confusing this.
So like the up and down, like the value here must be symmetric.
No, it doesn't need to be symmetric. No, you can set whatever value.
If rate of is true, and this is the value,
Yeah.
true, and this would not make sense because the rate of is true. Oh, is it because like could it be possible like the logic is true, like is could be like for both of them?
Yeah, it is.
Oh, in that case, it will need to be symmetric. Okay.
Yeah, let me draw a diagram here. So let's say logic is true. So logic is true, logic is 1. So now our notch, so we have notch active. We have two states, two possible states, notch active and notch deactivated, inactive. So we have these two nodes. What is going to happen? In this case, we have, because logic is true, we are dealing with these two numbers here. So we have a transition rate from notch up to notch down and notch down to notch up. What is the transition from notch down to notch up? 1. What is the transition from, sorry, I messed up. Notch down to notch up is 1, and notch up to notch down is 0. But you could have different values. If you had 0.1 here instead of 0, then this guy here would be 0.1. So this happens if your logic is 1. If your logic is false, L equals 0, then you have a different situation. Going from notch, from these two states would be different according to this. We would be choosing these numbers here. So notch will be basically the other way around, the way I wrote this. So this will be 0, this will be 1. All right? Fine. And then for delta, delta depends on notch in the same cell. So notch depends on delta on the neighboring cells, and delta depends on notch in the same cell. If notch is true, then we are dealing with these two numbers here. So the if a notch is true, it inhibits delta in the same cell. So upper regulation of delta is 0, the probability is 0, and the down regulation is 1. Because my probabilities are either 0 or 1, this is basically a deterministic network, okay?
Mhm.
This is not actually a stochastic network. So if instead of setting these probabilities to exactly 1 and 0, if you set to something else, then we are actually talking about a stochastic Boolean network, okay?
Mhm.
So this is like a special case of a stochastic Boolean network where our probabilities are either 1 or 0. This is a deterministic one. But in essence, if you change these probabilities and have them not be 0 or 1, it's a stochastic Boolean network. And then you have like typical transition times. So if instead of 1, this is like 0.1, it's going to take a while for the cell to transition from notch 0 to notch 1. All good?
Mhm.
I guess we understand this, but this is more detail in case you need to look back at the slides.
Mhm.
And then we have our configs, our configuration. So to define the name of a parameter, we use the dollar sign. So for the average and the threshold, we have dollar signs for those. Similarly, we have dollar signs here when we use these parameters in our logics. If you were using parameters to specify the probabilities, same thing. You would use dollar sign and then like prob something, whatever the name of the parameter is. And of course, the initial state of notch and initial state of delta. Okay?
Okay. Of oh no, I was just like think it's funny that these variables have a method, like a method also. Oh, it's okay because I thought the variables were not
Oh,
have
yeah.
a dot.
Oh, but you absolutely can have in Python, you can have yes.
Delta is a value here.
Yeah, this is C++. Delta is a node. This is a C++ object and it can have it has attributes.
Okay, it's a okay.
Yeah.
Yeah, no dot. Attribute. Yeah.
All right. Then similarly to Tellurium, you do add mapbus to cell.
Mhm.
Very similar to what you do in your code, but with mapbus instead. Yeah. Yeah, this is how it looks like for cell in self.cellist. Then you have you attach mapbus to that. There is these two parameters, time step and time tick. I don't remember what they are. Let me see if I wrote in a slide here.
I'm also very interested on the BND strand. I know like this is for configure. Oh, this is a Boolean network. Right. Like Boolean network would. So what am I going to import here?
Yeah, we have two strings here. So this BND string, that's your model specification. So it's basically this thing here. And then this is the config string which you're going to say here, delta notch config. So there are two strings, one for the model, the nodes, another one for the initial states and parameter values.
Okay.
Then you have time step and time tick. if I remember correctly, time step, you basically always set to 1. And that's going to rescale the probabilities. So if you set to something else, it's going to rescale the probability rates for you. So usually we just set time step to 1, that's it. Time tick, if I remember correctly, is how many times you call MapBoss model for each Monte Carlo step.
So what is the in Tellurium model, the time step performs the role of the time tick here. Because I remember professor told me last time that the time step is related to how many times the antimony model will be called in one monocle step. And now, like you're saying, the time stick is playing the role in a delta. Oh, no, delta. No, it's just a word. It's not delta. No, MOBOS model. Is that correct?
Yeah, this is what I said, but I could be wrong. I'm not sure.
Okay, we could just
Okay.
look it up.
Yeah,
after
but
this.
the simplest way to dealing with this is set both to 1 and then nothing
Mhm.
scales. Okay?
Okay,
That's the simplest way of doing things.
yeah.
This is what I always do. I set them all to 1, that's it.
Mhm.
Nothing to worry about.
Mhm.
And then you set a random seed because you don't want everything behaving the same way if you have a stochastic one. Of course, in our case, doesn't matter because our network is deterministic. Okay? All right. So we have our list of commands. So instead of saying cell.sbml, you will say cell.mabos, but it works the same way. And then you say, to retrieve the value of a node, you say cell.mabos dot the name of the model, and then square brackets and in parentheses, sorry, in quotes, the name of the node.
Mhm.
So it's the same syntax. It's just instead of SBML, you were saying Mabos.
So, okay.
No, yeah, this is the name of a
Okay,
node,
okay.
and ICD is the name of the node. The only thing that is different, and this is quite annoying in my opinion, is that to change the value of a parameter
Mhm.
of your MapBoss model,
Mhm.
you have to use this one here, cell.mapboss.mymodel.network.symbol table, and then the name of the parameter.
It probably just recreate a new matrix, like a transition matrix for right? Because it just didn't replace a parameter in situ replacement. Instead, I think it probably just create a new node. It's an index.
This is because MapBoss treats parameters and nodes differently. Nodes are Boolean, and parameters are floats.
Yeah.
So to change the value of a node, you use this syntax here, cell.mapboss.mymodel, and then the name of the node. But if you want to change a parameter,
Mm.
then it doesn't treat it the same way. And then this is the syntax. And I wasn't the one who developed this, so I can't explain why.
Okay, thank you. Probably just because like it's going to be a matrix, right? If you imagine all of the
Yes.
transition probabilities of this network is going to be a matrix.
Yeah.
So it's like a table. So
Yeah, but this
probably
is
that's
for the oh yeah, but you could have many parameters and they don't actually form a matrix because for example for example here I have DAVG greater than D threshold. I could have DAVG greater than D threshold plus something else, plus something else, plus something else.
So you
So-
mean like you're adding some customized parameters?
Yeah, exactly, yes.
Yeah, but that's not the transition. So
Exactly.
yeah, so probably they have different
Yeah,
ways to restore these.
yeah.
Okay. I see. Anyway, I have to remember this.
No, you don't have to remember because it's in the code snippets.
Yeah,
You can access in the code
just
snippets.
to just okay.
Yes. So this is how it's going to look like. It's very similar to the one you already have, with the exception that here we do dot mabos dot the name of the model, dot state. Oh, there's this. Oh yeah, dot state to get the actual value 0 or 1, and mabos dot delta notch dot network dot symbol table DAVG to pass the value of the average after you do the average among neighbors. And then the rest is the same. Like you have a loop over cells, a loop over neighbors, and then you do the tracking. Okay? You do a time step mabos the same way as you do in Tellurium. And yeah. I think this here has all the information and the instructions summarized. So instead of going back and forth between the slides, you can look at this slide. And that's the exercise. Of course, the number is incorrect because I was lazy.
Number?
The number of the exercise is 8,
Oh.
but we are doing lecture 13. Yeah, so just ignore that. So your exercise is to substitute your Tellurium model by a MABOS model, and I would recommend you to version your simulation so you can preserve this for future reference.
Just so this one to
And I mean, the slides I'm giving, they are basically giving the final answer.
yeah.
So I don't know what you want. Like, do you want to not have the slide and try to solve by yourself, or do you want to use it as reference? Because I don't think it's like, I think passing the code is just an annoyance, and I can actually copy and paste the code for you if you want in the chat. Because then we can, you can,
But I have to like copy the model string because I was pretty unfamiliar with the SQL tools.
Yeah. Okay, okay, I give you the model string and then
Okay.
and then you do the rest. You want me to give you the
Model parameters.
add the maples to cell thing?
Marbles. I think it's okay. Oh. Is it like it's circle and what engineer? Yeah, it's called engineer.
Do some new lines, like to help with seeing these configurations. Yeah. And then I like to do this.
Oh. Okay.
It's easier to see. Dot state. And it's a delta, not a D. Yeah.
No.
Mhm. Yeah, this is the ugly one. Network, Mavos delta notch, network, symbol table. Delta?
Oh.
Is it model one the name?
Yeah.
Not there. Scroll down.
Model.
Model, yeah, it is. Yeah, model name equals
Yeah.
model one, yes, that's
It's
correct.
moved by that. And about the threshold, so it's here. Okay.
Yeah,
So I don't need to do update for the threshold because it's settled, it's fixed.
correct.
Okay, and only the average for the surrounding data is updated. I think that's alright. Yeah, I think that's alright. Let me just try that. There's not that. Please.
It's fine, run it, because I think you were initializing the value.
No, I think it's already like after a step. Where it's not the, oh, it's the first step.
Are you sure you're running the correct simulation?
Yeah. Um,
Could you screen share again, please?
okay.
Okay, run that, let's see. Cause 0.5.
Mhm.
And yeah, let's see notch.
It's all 0.
Oh, this is the tellurium one. Yeah, you're not running the correct simulation.
But I annotated this one. Oh,
Yeah, but you're
probably-
running the,
yeah, probably
yes.
the players. This one, okay. Oh.
Okay. Model, cause I probably wrote model, not model one.
Model string.
Oh.
Oh, it's delta notch.
Delta notch, yes. Delta underscore
Mhm.
notch. Model string equals. Oh, I don't think that
I think it's like.
no, no. That doesn't.
What's it?
Oh, wait, model name. Model string, there is no model string in it. Just delete that.
Oh,
Yeah.
it's only BNB string. Model.
Yes.
Okay.
And model name, yes. And oh, there is also, oh yeah. Yeah, that's all. Yeah, where is the delete here? Oh. Oh, I messed up, okay. Yeah, that's it.
And spell unexpected keyword BNB string.
BND STR,
Yeah.
STR. Yeah,
So, no, it's
what's the line? Go straight to the line. Line 88. My boss, that's the annoying one. It's mabos dot delta notch dot network dot symbol table. Because you're changing a parameter, not a node. The AVG is not a node.
Oh.
So that the syntax for that is cell dot mabos dot delta notch. Yeah, model one, yes, dot symbol dot network dot symbol underscore table. DAVG equals, yeah, that's it. Yeah, let's try that.
It didn't report any error in one.
Let's run and see what happens.
Okay. Mhm.
Oh, this is interesting. Show notch. Let's see notch, what's going on. All right, let me show me your network.
We copied the network
Oh, okay.
and
Yeah. Surface area. Let's for the initial condition, I want you to initialize random values of delta and notch. So right here I have cell.mabos.delta.state equals Boolean random choice between 0 and 1. So it's going to initialize random values of delta and notch. Yeah.
NumPy is built in the
Yeah, I guess maybe.
Mhm.
NP dot
random dot uniform.
no choice.
Okay.
Yeah. Parenthesis, square brackets, 0, 1. Yeah. Now you transform that to a Boolean, so bool, and then parenthesis. Yeah, bool,
Oh,
BOOL,
okay.
and everything in parentheses.
So I have to do
Yeah.
this again for the.
Yeah, no, this is enough. I mean, you
Okay.
just need to randomize one of them. Yeah, this is enough. Try running.
Okay.
Oh, this is in, yeah, this is correct. Could not delta, no, oh
I
yeah,
didn't add the model.
yeah, model 1. No, delete delta notch.
Wait, oh.
The name of your model, yeah,
Okay.
yeah. All right, now it's randomized. There we go.
So why would you think like the first piece would show up?
Why was like blinking like that?
Yeah, like all the cells are blinking
Yeah,
at
yeah,
the same pace.
yeah. I think so. They were all. I don't know. I don't know what you. I think it's probably. I don't know.
Or
Yeah.
but like in the SBML model, we didn't see like that same even once. So that.
Oh yeah, but I don't know what that is.
Okay.
They when I run it, I'm pretty sure they don't blink. So I don't know what's going on. I can try here. And as an exercise, put a a threshold of what you are seeing delta, right? Set threshold to 0.9 and run again and watch what happens with delta.
I guess we can slower for it to have a pattern. Like
Yeah, did you run?
I didn't run, but let's
Okay.
just make a guess.
Oh, what are you guessing?
I think it will be slower to reach a
No,
threshold.
that's wrong. Guess again.
Um, Alright. Okay.
Hmm. Guessing?
And then the guesses will never reach like a pattern because the threshold is very high. And for solid, that all like almost mean like all the neighbors need to be delta. opposite.
Let me try to guess with you. So we have D threshold, DAVG has to be higher than D threshold for notch to go up, right?
Mhm.
So when you set D threshold 0.9, we
Mhm.
have to have a lot of delta cells around the notch cell.
Mm.
So here we have very few delta cells. So the opposite will have to happen. We need a lot of
Oh.
delta cells. So the notch cells will be the isolated cells, and the delta cells will be the ones surrounding the notch cells. Does that make sense?
Makes sense, but well, question is how this a system reach like a stable status like that? Because like the no the initials like initial condition for both delta and notch are zeros,
No. You are setting random initial conditions.
and now like we're
delta.
just like set delta a little bit higher. So it's
Yeah,
randomized.
but again, you just need one cell being different, right? If you scroll down and instead of doing the Boolean, if you do this, my God. And run, it's going to generate a pattern. Yeah, only one delta cell. And I don't know why it blinks like that. I have no clue. But it should be spreading the pattern. Oh, look, it's the pattern is spreading.
Mhm.
I don't know why it blinks. I have no idea. But now you can see that the delta cells are the ones surrounding the notch cells because you set a high threshold.
Okay. So if we're a delta like larger, it's larger. Delta node. Oh, what is the notch node and delta node here? Like for a cell. Larger. So what does that mean? Like a node delta whose logic is not.
So if in this case here, if notch is up, delta will go down, and if notch is down, delta goes up. Notch, again, notch inhibits delta. So logic being notch is basically saying if notch is up, you have these rates here, these two rates here.
Mm.
So up rate of delta is 0 if notch is up, and down rate of delta is 1 if notch is up. If notch is down, then you have the other way around. Oh, that's why it blinks. Oh, so it makes sense. Yeah, that's why it blinks. Because when notch is 1, no, I don't know why it blinks. I don't know. But it works. There is some refinement I have to do to this model. But it achieves the pattern nonetheless.
So for both for delta and notch they were going.
You're trying to understand why they blink?
Yeah, I think I began like to understand
Yeah,
about the
maybe.
structure, but yeah, like the blinking thing is
Um,
Mhm. They're like right now like all delta because like the notch values.
yeah,
together.
they are all delta. When they are all delta, what happens is notch goes up, and then when notch is up, delta goes down. And then when delta is down,
For every cell, like for every cell, single cell here, the delta average would be on the threshold.
either 0 or 1. Yeah. So in this case right here, like these cells here, they are all delta equals 1.
So they all want to like transfer to.
They all go delta, they all go notch
Notch.
equals 1, and then delta goes 0, and then that's why it blinks. Yeah, that makes sense. So if we don't want the blinking, let's try one thing. Instead of having 1 as the rate up, let's set 0.1. 0.1 as the rate up, and then 0.1 as the rate down. Everything 0.1, where we have 1. So this is an actual stochastic network. And here too, we have a 0.1 here, a 0.1. And line 30, 31. So now, I mean, it's still probably going to retain some like blinking stuff, but not to the same extreme. Oh my God.
I think
Oh
we
yeah,
need
it
to-
just takes longer to.
I think we need to randomize the. Oh wait. 0.1. So maybe this is a little bit too.
No, yeah, this is fine. I think it's always gonna blink, honestly. It's always going to blink like this. Yeah. I don't think there is a way around it. Yeah. And but it just takes longer to spread the pattern because of the probability of sats is a little bit lower. A lot lower actually. Yeah. Yeah, that's very fun. Yeah. The blinking is actually it is actually uh uh an annoyance of the Boolean stochastic network. Yeah, that's how it is.
Yeah, that means like the cell, the tissue is like synchronized. And it's like, but let me try to like
Yeah.
add some.
Yeah, if you randomize everything, then yes, then you, yeah, we revert back to bool.
Um,
np.random.choice. Yeah. Then that should kill the blinking. I mean, the cells will still blink because that's what the Boolean network does, but not like not synchronized like that. Maybe a little bit synchronized.
because like
Try randomizing the notch as well, because we are just randomizing delta. Yeah, this is what I have in my original simulation. I randomized both, and then there is no weird synchronized blinking.
I think it's because like there are still clusters.
Yeah,
So but now you can see like it's not very.
yeah, because the clusters are smaller, but clusters will blink together.
Yeah. So
Yeah,
like the single cell blink expands to like the whole aggregate.
yeah,
Like,
yeah, true.
that's interesting.
Yeah, and yeah, it is an artifact of the Boolean network. Like in the case of tellurium, it's as if they are all the same. No. Yeah, I think I have to refine this MapBus delta notch model. I mean, it works, it gets the pattern, but this blinking is probably not realistic. So this is to show that MapBus does the job of achieving the pattern. So if you are trying to decide whether you use Tellurium or MapBus, you have to ask yourself, like, what do I care about in this model? Do I just care about the final spatial pattern? I might go for a MapBus model, right? But if I actually care about the cells continuously transitioning between delta and notch levels, then you should go for a Tellurium model. Depends on what you care about. All right.
Mhm.
I think that's it for today then. We are 4 minutes over.
Thank you. Thank you, Professor.
Did you want to discuss the project at all today?
We actually had a meeting like next Saturday. Do you want to come to us, like join us?
Do you think we can meet another day, James?
Yeah,
This
well,
week?
I know you have another thing you've got to go to, so let's
Mhm.
let's make an appointment for a meeting. But tomorrow I have some time if you want.
Okay.
Your project.
Hmm?
Oh, we're talking
Uh,
about you.
Let's see what time would be good.
Yeah. If you do you want to discuss your project right now?
But
I think it's been a long afternoon, so it'd be better to do it
Yeah.
maybe tomorrow. What about noon tomorrow? Would you be available?
what is
No,
Are you asking me or
both of you.
sorry?
okay, that works for me.
I think that works for me. I will probably cancel APL's meeting anyways because I don't have the final thing. So yes, I think we can do tomorrow noon. Yeah.
Well, I mean, if you maybe want to, if you have something to show APL, you probably should do that. So
Because like we haven't
I could do Thursday morning too, which is better for you.
Saturday morning?
Thursday or tomorrow.
Thursday or tomorrow.
but
No, it doesn't hurt to
Joe,
discuss it because
what's
but
better for you?
James won't be able to attend the Saturday meeting with Maciek and Pete.
I might, but I don't know. That's all.
Okay.
what about this Wednesday?
Let me put it down for tomorrow, and then we could always change it
Yeah. Yeah, tomorrow
if
noon.
it doesn't work.
Sounds good.
If it doesn't work for you, that's fine. Just let me know and we can change it. But I'll hold the time at least so that in case in case you unless you want to. Thank you, Pedro. Thank you very much. It was and you got through a lot of material today.
Yeah, no problem. I hope people had fun today.
Yeah. Well, I learned a lot watching the Mamba stuff. So okay. Thank you, everyone.
Thank you.
All right,
Okay.
thank you, James. See you
Thanks,
tomorrow.
Pedro. Bye.